So, right. So before we start the lab, I have to read something regarding the safety guidance for you. So you should wear at least the safety boots to start the lab. You all have it. So before beginning a test, okay. So you should consider very careful when you're using this grip because it's quite heavy. This grip is used for your POA sample, okay. So I will do it for you, but when you handle it yourself, you need to be very careful because it's quite heavy. Move up slowly using this hammer. Okay. So maybe this one first. Yeah, where the use this pin. Press down a little bit. Let's put it here. Okay, so when we deal with the upper grip. More. Okay. So before you start anything, make sure there's nothing in the testing area. Make sure that's clear. Okay, before we start. And another thing you should consider when you finish your setup, please drop down this seal. Okay. So if you're all clear about that, please sign this one for me. And we can start now. So you guys know what to do today, right? Your task. So first of all, you have to measure your dimension. I mean, from your specimen. Okay. So please tell me what kind of dimension you need to know before we start the test and why.
Gauge length.
Please explain. What else?
Sure. And the infill density.
No. Density is not a dimension.
The width.
Yes. What else? The last one?
The height.
Yes, the width and no, the thickness. Right? This way a little bit the thickness. So please tell me why we need to know about the gauge plane. What is gauge plane?
Distance between the stars.
Yes,
of these.
correct.
Yeah.
So why we need to know about the gauge plane?
Because we need to know how much it's changed from the
That's good.
origin.
That's good. How about the thickness and the width of? Tell me what width and thickness you need to know. This one or this one or this one?
In the middle.
Okay. What we call it?
Not sure.
A cross-sectional area. So why we need to know about the width and the thickness of that
It's
area?
going to stretch.
Stress and change during the test
Yeah.
as well, because we need to know about the original length of the specimen before we start the test, and then during the test for every point, every single point change the length, and you just divide the length by the original length, so you will have strength. And you need to know about the area because you have to divide the load by the cross-sectional area, so you have stress. Your task today very important to transfer from load and displacement, what we get from the test, and transfer it to stretch and strength curve. So you start from stretch and strength curve. Okay. So now we deal with your POA samples from 3D printing, which is very brittle, and then we also deal with the aluminum specimen. And it's different. I mean, the geometry is different from your POA specimen, and we use another fixture, another press, which is this one. Okay, so I'll guide you later. But the purpose is to combine them together, compare them together, and you see what is different when you deal with the plastic specimen and metal specimen. And also when you deal with very brittle material like your POA and very ductile material like aluminum. That is the task for today. And before that, as I said, you have to measure the dimension of it before we can like climb on the machine. Okay, so what else for your homework? After that, when you attend the strength and strain curve, try to find the tensile strength, ultimate tensile strength, and Young modulus, and yield strength, and failure strength. That's all. Okay, so combine them together, see which one is higher than the other one, and I will explain for you why. Okay, and because the reason they increase the density to see whether it's become stronger or weaker compared to the lower density. Okay, so please help me to measure the dimensions of every specimen, but be careful with this one because we cannot attend the gauge length now. You can only know about the gauge length until you mount on the machine, and then you just measure the distance between two heads. But for aluminum, you can like measure it right away. You don't have to wait because you know like the gauge length already there, cannot be changed. But for this specimen, depends on what position you mount, you climb it. Some people they climb from here. Some people they just change the length doing this area. So we don't have average value at the beginning, but you only know when you climb it on the machine, and then you use your caliper to measure the distance between two heads. You know what I mean? Because we cannot. Can you use this caliper to measure the gauge length? No, right? But you can use this caliper to measure this length, right? Am I right? So basically, just the width and the thickness for your POA specimen, and the diameter and the gauge length for aluminum. You know how to use this caliper?
Yeah.
Okay. So please use to measure for your POA sample first. It's recording. Okay, so see, it's not the right way. Okay, if you want to measure the thickness, for example, I climb like this. Okay, so I reach from the zero of the lower ruler. You see, it's around 5, I guess. No, it's not 5. 3 for the thickness. Okay, see from the zero. And the width will be 13 for the width. We don't know about the gauge length yet. Okay, and for aluminum, we start with the diameter, and we do the same thing. And I can see that from the ruler, the caliper is 5 for the diameter, 5 millimeter. And the gauge length, we use this feature for internal dimension. And I put it here. 27 for the length. Okay, aluminum. You have to write down because when we use the software, you need to remember the dimension. Okay. So we start to mount the sample. So please remember the principle. You have to deal with the lower grid first, and then when you finish the lower, you deal with the upper later. All the time. Okay, so I open it. With the sample, I start with the first 25%. So the mark is the first one. Okay. I deal try to mark from here, okay? Try not to clamp too tight, just tight enough. Otherwise you will break the specimen. Okay, so I move below the upper. And be careful because the head will touch the specimen. When you move down, be careful. So now you have to make sure that your specimen, you know, is in vertical direction. So I will adjust a little bit. Precision and then yeah. One. Just tighten up. Check your specimen. Okay, it's tight enough. So I use the caliper again to measure the gauge line. Okay. And the length will be 76, 77. Okay, so we finished the setup. Let's drop down the seal. Okay. Can you come closer? Now we deal with the software. This is the software for this machine install machine. So I start click on test here. Okay. And you click close. This will put over the speaker. Okay. Close. And then name your file. This is the POA's first POA. I pressed first, and then 25%, and I put it today will be what day is it? 17. Yeah. 03 and 20. Okay. Okay. And then you can see that this machine can deal with not only tensile testing but also flexural compressive. In this case we do tensile. And you have to choose the unit, which is the SI unit. We use a millimeter, Pascal, gigapascal, megapascal, so on. So we choose SI units. Click OK. This function is used for composite as well. So we don't care about this one because we deal with the POA. We don't care about how many percent. So in case you test for composites, they need to know about how many percent carbon fiber you use. In this case, just click OK and we confirm the file. Okay, we create the file. Then we click on defaults here. See? And you click on parameters. Okay. And we have the standard. In this case will be American standards, ASTM, American standard. And the width we already have how much? 13. Okay. The thickness we have 3, and the gauge line we have 77. The crosshead speed very important. So basically, when you test the sample based on the material you use, the ASTM standard will identify the suitable speed. In this case will be the speed of the upper head moving up. Okay, so in this case for POA is quite brittle. I want to use low speed because you want to make sure that the test duration will last for around 30 seconds. We don't want it last for so long or for too short. So basically 30 seconds is good enough. So I choose millimeter per minute. I mean the speed of the crosshead. And the data rate will be the value generated for each second. Okay, so in this case it's to 1. Okay, So we finish everything. The last step, you set the load and displacement to be 0. Just click here. You see it turned to 0, and the displacement as well. So you can start from this position. Okay. So you can start the test here. Check your dimensions again, and click OK. And click OK again. So you start the test. When the test finished, you click here to stop it. Okay. If you want to check the speed during the test, just click here and you will see it too. Okay. So if something happen here, and pay attention for this load. Try to check whether the maximum load this specimen can bear during the test. What is the maximum load? So yes, you can check the test. You see it now reaching 1 point and it's dropping. Okay, so we stop here. The crosshead will return manually. Click OK, and see this is your first result. You can check the modulus here, but you have to calculate the young modulus yourself by yourself. Okay, but you can check here. You can write the value if you want to check whether your calculation is correct or not. But you have to calculate the young modulus by yourself. Okay, so end the sample and click continue. If you don't have any comments, just click OK and then OK again. So we have the first file, no, click no, and then if you want to check the stretch and strength curve, you can click on graph, click OK, and this is your first stretch and strength curve for the first 25% POA sample. Okay, so when we test another specimen, then we'll combine them together to see what's different between them. Okay, so click on File and turn back to home screen and start a new test. So I will continue with aluminum. I'll continue with aluminum, and then for the next POA sample, you have to test by yourself, but we don't record it. Okay, because do the same thing. So I will deal with the aluminum and you record it, and we combine the result together and we stop the recording. Okay, so now we have to remove the sample. So because it's POA, so it's safe, we don't have to care, but sometimes we deal with metal specimen, the proton error may be very sharp, so please pay attention, be careful. So as I said, we deal with the aluminum specimen, we have to change to another grip, so I remove it. Be careful, it's quite heavy. Pull up the pin. This grip here, presses, pin now, remove it, and we change to another one. close enough. So here we have to deal with the aluminum specimen. For the first one, you will see it has one pin and two rings. The first ring will be rubber and the second one will be steel. Okay, and another two half of the grips. Okay, put your specimen here. You have like a T-slot right there to clamp the specimen, and put another half here. Always remember, put the rubber ring first here at the bottom, and then the steel ring here. See, and then once on the machine. Fluid. Okay, so we move down a little bit. Okay. And we use another grip. Put it here. Okay. The rubber ring, the bottom, steering. Okay, use your two fingers to hold the sample like this, and then move the crosshair down until the 2 points at the same position, and then you can put through the pins. So now you check your sample again and you still feel it's slack here, so we cannot start from this point. So the only way to make it tight, you have to use panel to move the crosshead up one step at a time, very slowly. Okay, to make sure that it's tight. So you can check the panel over there. You can see the value of the load now is minus 0.06. We need it to be nearly 0 before we can start. So I move up. You can see that the loads increase. Okay, a little bit. Yes, we can start from this one. So I check the sample again and I can feel a little bit tension here. It's tight enough. So we can start from here. Okay, it's more. Okay. And we drop down the seal. Deal with the software again. Click on test. Okay. And I name it aluminum. Tensile SI units. Okay. Okay again. Okay. Dimension will be 5, and the thickness will be the same 5, the same with the diameter. The gauge length will be 27, and because we are dealing with a very tight material like aluminum, so I suggest we use a higher speed. In this case, we choose 10 instead of 2 in case of POA specimen. And click OK. Set the load to be 0 and displacement 0 as well. And start the test again. OK. And I start it. Please record it, the configuration. So basically you cannot see any necking state on a POA specimen, but on aluminum you can see very clearly. I mean the necking stage. And we can remember that from the POA sample, the maximum value for the load will be 1.1. Try to see. Okay. Okay, it's broken, so we can stop the test. This is your aluminum sample. So you see the young models now is higher, right? 3,000, more than 3,000. So I stop and the sample, continue. Okay. Okay, again. So the important part, we have to combine them together. I click here, you have like stress and strain curve for aluminum. I try to combine them with my PLA sample. So I open PLA first, and then 25% here, the file. Combine them together, you can see the difference between them. So basically, this is the elastic region. You can see from this point to this point will be a line, right? A line, then it's straight to the U point here, and then it turns to plastic region. You know the difference between elastic and plastic deformation, right? So basically, elastic is something related to when the specimen deform and then it can turn back to original stage. But in plastic region, it's kind of a permanent change, so it cannot turn back to original stage. So this is for aluminum, the blue one, and this is for your PLA, the red one. Okay, this is U strength, and this is the tensile strength, which is ultimate tensile strength, and is the failure strength here. So please don't use this range. Everything stop here, okay, from the failure point. Okay, so can you tell me what is the difference between the aluminum and your PLA? First of all, you have high tensile strength, which is the strength of the material. So when you hear some people say that this material stronger than the others, means it has high tensile strength. So in this case, tensile strength identifies the strength of the material. Okay, and another thing, you know what is Young modulus? You know how to calculate it? Basically, it will be the gradient of this line. Okay. So the gradient, higher gradient means higher Young modulus. So Young modulus identify the stiffness of the material. So you understand what is the stiffness. So I will give you an example to explain what is stiffness. When you apply the load, you know, like I just assume that this one and this one will be the same, the geometry, everything, but different material. So I call it material A and material B. When I apply the load, you can see I can easily bend it. But for this one, no, it's very hard. So I call it the B one has higher Young modulus or higher stiffness than the A one. Okay, just assume it's the same, share the same geometry. Okay, that's the meaning of Young modulus. So Young modulus means the stiffness. And another thing, you can see that first time you see the stress and strain curve for both PLA and aluminum, you will see that the aluminum specimen can last longer. I mean, during the test, last longer. You see, this distance kind of longer than the PLA. In this case, we can call it aluminum is more tight than PLA, or PLA is more brittle than aluminum. So the distance from the U point here, to the failure point identify the ductility of the material. Okay, so three things I can say about this stress and strain curve. I can say that aluminum is stronger than PLA. Okay, stiffer than the PLA as well, and more tighter than the PLA. You can also identify the toughness. The toughness is kind of the area of the whole, the area here, the whole area. Identify the toughness of the material. Basically, it's the maximum energy that material can absorb until it's broken. So you see that this area is much smaller than the area of aluminum specimen. So I can say that aluminum is tougher. So, but in this case, we only care about the Young modulus, tensile strength, and the ductility of the material. Okay, so you will try to test for the other to see what change when you increase the densities inside your POA specimen from 25% to 50%, whether it's stronger or weaker. Okay, so